Good morning, respected organizers, session chairs, dear researchers, and academicians. I'm Engineer Aditya Singh, ISDS. I've been an independent researcher, editorial review board member in 6 American international journals: IJSSMET, IJPAE, IJRLADM, IJSDS, IJPE, IJDSST, IJESGT. Reviewer in 10 American international journals, 5 Singaporean and 1 Indonesian-based international journals, as well as research mentor at Academy Nova World, Kalipur, India, alumni mentor registered by Amrita University Alumni, Amrita Vishwa Vidyapeetham, India, and ex-alumni mentor LPU. The topic of today's presentation is the necessity of bioengineered and microbial materials in the field of construction. Outline: today's presentation will cover the following outline, which will include introduction, literature review and research gaps, methodology, results and discussion, and conclusion. Introduction: general. The construction sector nearly contributes 37% or approximately one-third of global CO2 emissions, with cement alone accounting for 7 to 8% of total emissions worldwide. Despite advances in high-performance concrete and composites, durability loss, cracking, corrosion, and frequent maintenance continues to dominate infrastructure cost. So there's a fundamental question: can construction materials become adaptive, self-repairing, and environmentally regenerative rather than extractive? And bioengineered and microbial materials offer one uh, such pathway. Then the limits of traditional construction materials. They are considered insufficient presently because of the core technical limitations. The concrete cracking is inevitable because of the shrinkage, thermal stress, fatigue, which happens. Then leads to the reinforcement corrosion, which is another drawback. And the maintenance dominates life cycle cost. The repair can exceed 2/5 to 3/5 of the initial construction cost over lifespan of the structures. Then carbon intensity is like the ordinary Portland cement. They are having around 850 kg carbon dioxide per ton. And then static material behavior, no adaptive response to damage or environment. So the traditional materials are passive while infrastructure operates in dynamic environments. Literature review and research gaps. Uh, Out of the 40 published research papers, the recently published one were taken into account, and the existing limitations are long-term bacterial viability, regulatory hesitation, standardization of gaps, and scaling from pilot to mass infrastructure level. So the existing literature, they have shown that the microbial and bioengineered materials can reduce CO2 emissions compared to OPC, can improve durability and crack healing, have been validated to laboratory and pilot scale, and there have been documented technologies for MICP for soil stabilization, bacterial self-healing concrete, mycelium-based non-structural materials, and biocementation for permeability control. But The regulatory challenges, regulatory uncertainty, long-term performance are unknowns. So this study does not claim the discovery of such materials, but it claims the integration, evaluation, and synthesis, which the existing literature is weak. Then there's fragmentation of evidence across disciplines, as the civil engineering literature focuses on mechanical performance, while environmental studies focus on carbon reduction, and biotechnology papers focus on microbial behavior, whereas digital construction literature treats materials as static inputs. So presently, there's no single framework which could link structural performance, environmental impact, life cycle cost, and digital deployment pathways. So the relevance of studies is the synthesis of structure engineering metrics as well as sustainability indicators, deployment constraints, and digital optimization potential. So these disconnected research silos could be integrated into one and could incorporate it on a larger scale in the future. Then the lack of then the cross-regional evidence were also considered as these materials where they are predominantly used were taken into account and so on. Methodology literature review for the recently published papers from 2020 to 25 were considered for bioengineered and microbial materials, especially in the context of construction, and the case studies of countries like Denmark and USA, Netherlands, and Singapore and India, where such materials are being used, and market and future scope covered with the assistance of graphical analysis. Now, microbial and bioengineered materials, uh, MICP, they are being used in Singapore and India. And what it is basically a bacteria, Sporosarcina pasteurii, which could produce calcium carbonate. They are used for soil stabilization and biocementation. So they are able to help in soil strength increase from 2 to 5 times UCS improvement, and the permeability reduction could be up to max 90%, whereas they are also used in ground improvement trials in Singapore MRT projects and IIT linked trials in India for sandy soils. The benefits, the benefits. They reduce cement uses, lower embodied carbon, improvement erosion resistance. So MICP is not experimental anymore, but it is field tested at pilot scale. Then self-healing bacterial concrete. They are primarily used in Netherlands. They are encapsulated bacteria plus nutrients, activate upon crack formation and moisture ingress. And the crack sealing could be up to 0.8 mm, water permeability reduction by 80% max, and life expectancy increase from 30 to 50%. They are being applied on bridges, marine structures, tunnel linings, and they convert maintenance heavy structures into low intervention systems. The mycelium based construction materials could be seen on the figure right hand side. They are primarily used in USA and Denmark. The material properties offered by them are lightweight, fire resistant, compostable, grown, not manufactured, and they are being applied for non-load bearing panels, insulation, temporary structures. So the environmental evidence could be seen that there's near zero embodied carbon, no high temperature processing. So they are redefining what manufacturing means in construction. Then biocementation and carbon negative materials. The figure shows one of them on the right hand side. Basically, they are bio-based binders which replace clinker and carbon mineralization via bacteria, while life cycle carbon dioxide reduction from 20 to 70% depending on the mix created. And these materials complement, not immediately replace structural concrete. Performance, cost, and life cycle evidence. Durability wise, it could be said that they reduced crack propagation, slower chloride ingress, enhanced tree thaw resistance. And cost wise, it could be said the initial cost increases by 10 to 20%, but the maintenance cost reduces by 40 to 60%. So the overall cost also reduces, which is good. And the sustainability metrics, the carbon dioxide is being reduced by using them, and extended service life could be achieved while reduced raw material extraction could be done. So bioengineered materials become economically viable only when life cycle performance is considered, not initial cost alone. In the coming years, of course, AI optimized bacterial deployment, digital twins for biological materials, biobinders in 3D concrete printing, and performance-based codes instead of perspective ones uh, could be explored further. As these solutions are early stage solutions to real, measurable, and construction failures as of now. Results and discussion. Figure 4 shows the growth of MICP worldwide. And in the year 2024, the market value was 312.5 million US dollars, but by year 2033, it is expected to reach 1.17 billion US dollars. So it could be said that the increase is almost 5.8 times in the span of just 8 years, in the span of 9 years. So, which is a significant increase, and it shows that MICP could be invested more in the future, and it will be a wise decision to use them in uh, construction projects at a large scale in the coming years. Then figure 5 shows the growth of self-healing concrete where in the year 2023, the market value was estimated as 84.59 billion US dollars, but by year 2032, it is expected to reach 1.038 trillion US dollars. So it could be said that the increase uh, is massive, uh, and just in the span of 9 years, and self-healing concrete uh, investment will be uh, uh, wise decision in the coming years, and incorporation of them on different projects will be beneficial. Then figure 6 shows the growth of mycelium-based building materials worldwide, uh, which has the market value of 910 million US dollars in the year 2024, but by year 2033 it is expected to reach uh, 2.5468 billion US dollars. So it is roughly expected to increase by uh, 2.5 times, 2.67 times, 2.6 to 2.7 times roughly, which is a massive increase in the span of 9 years. This shows the high demand of mycelium-based building materials uh, in the near future. So it will be a wise decision to invest in them and use them for temporary structures for not load-bearing panels in construction projects. Conclusion: the conventional construction materials and their limitations were highlighted. Then the bioengineered and microbial materials concept was discussed, and how they could be applied in construction, and primarily in which particular countries they are being used, the current gaps and the utility of this study were further covered in this presentation. Then how the market and future scope through graphical analysis were taken into consideration. These are the key references. Thank you.